Hi guys, Miss Redigan here, and we're going to be focusing in on gases. We've learned that gases have a lot of space between them. They're moving very quickly. There's lots of randomness. They have high entropy, weak intermolecular forces. They're moving so fast and far apart. We've learned they're compressible. Okay, so we're going to take some of that knowledge and be able to start making predictions. Right? Because if you can make predictions, then eventually you can start manipulating matter. Okay? So let's take a look at a balloon. Okay? So a balloon is a great example of a gas in a container that we're all kind of familiar with. So I want you to imagine, right? These particles are drawn, not moving, but you have to imagine them whizzing around, sort of like the little lottery balls in the lottery machine. Okay? So they're whizzing around in there. Now, what happens if it's a really hot day out, let's say? Okay? I know, my lovely drawings. It's really hot. What is the heat going to do to a particle? How is that particle going to start moving if there's heat added? Right? You're adding energy, that heat energy. Okay? Make a prediction. Okay. So you should be saying to yourself, oh, they're going to be moving even faster. Okay. Now, if they're moving faster and it's in a balloon, well, a balloon doesn't have a fixed volume, right? A balloon, that rubber or latex or the plastic mylar, whatever kind of balloon it is, the size of that balloon can change. They can flex, right? So volume isn't fixed. The volume can change. So if they start moving more rapidly, they're going to start spreading out. And they can actually make the balloon get a little larger. Same number of particles, right, in the balloon, but now it's a little less dense, right? And the particles are moving more quickly because of that added heat. And then think about it, that's how a hot air balloon kind of works. You add extra heat to the gases and they become less dense and they can float high in the air. So you have the balloon, you have the gas, you add heat, you have a non-fixed, a flexible volume or flexible container, and that will actually increase. And the opposite is true as well. You can think of, if I take a balloon, if you've ever bought a balloon in the dollar store one day, and you go outside and it's really cold out, the balloon, if you ever notice, sort of like, looks like it's deflating a little bit. It's not losing any of the helium they put into it. It's not losing the gas, not leaking out. Because if you go back into a warm room, it kind of puffs back up. So if you add heat, the volume can get a little bit bigger because of that extra energy and that extra motion. If you remove heat, they will actually come closer together, and it looks like it's deflating when it's actually not. So temperature can definitely have an effect on volume if it's a gas. Remember, only gases are affected by these things because gases can be compressible or not. Okay, so that's one stage. Let's think of something else. Okay, so let's take a look at another situation. We're still going to stay with the balloon, right? Again, a balloon does not have a fixed volume, but it can be affected by temperature. But what about pressure? What if I apply pressure? I know you're loving my artwork, right? What if I applied pressure? If I pushed on the balloon, what's going to happen to the size, the volume of the balloon? Think about it. Not so much that it explodes. Okay, so all of you have a picture of what that would look like. I hope in your mind that it would get a little bit smaller. Right? You can compress, like in that syringe I showed you in the demonstration the other day. I can compress. So if I add pressure, the volume decreases. Okay? So I can push down and decrease that. And it's going to make the gas particles a little bit closer together because the volume's a little bit less. So if I add pressure, and vice versa, if I let go, come back to here, right, it's going to enlarge again. So I push on the balloon, I can apply, add pressure, the volume decreases. I can let go, remove or decrease the pressure, and the volume increases. Okay? So always kind of think of logical things. Now let's do one more. Okay, Let's take it scenario number 3. Let's see if a can of spray paint or any sort of pressurized can, okay, could be whipped cream or hairspray, whatever is pressurized gas. Okay, so if you look, there's always a warning about not putting it near heat. Okay, so why? Let's think about that. Let's look at the particles inside. Now, in these cans are pretty sturdy. So the volume here is definitely fixed. The volume's not going to change, not like the balloon. So the volume's not going to change. But let's see what else is going to change. So let's add some heat, right? Imagine these are whizzing around, but now we're going to add heat. We put it near a fire, or we leave it near the sun, whatever, a radiator. If that gets near heat, think about how the particles are going to move. Are they going to move faster or slower? Think. And hopefully you're saying faster. They're speeding up, right? Adding heat energy is going to allow them to move more quickly. And in this case, they can't spread out. They have a fixed container, a fixed volume. So if they're moving more quickly, they're going to be hitting the sides of the container more frequently. And when gas particles hit the side of their container, they create pressure. The more frequently they do that, that's an increase in pressure. So let's go back to the warning. If you put this pressurized can with a fixed volume and gas particles near heat, the particles inside are going to speed up. They're going to collide with the sides of the container, increasing the pressure inside. Eventually, what's going to happen? Think. Eventually, that pressure inside will be so great that can's going to explode. Okay? You can probably YouTube this. Do not do this yourself. Right? If you put a spray paint can in like a fire, do not do that. It's very bad. Okay? It will explode. Okay? Maybe I'll find a YouTube video because I do not want you doing that. I'm very, very hurt. Okay, so in this case, increasing temperature increases the pressure. And if I remove that, if I get rid of the heat, right, these guys are going to slow down in here, and the pressure is going to go down. So always be able to think in both directions. What is adding heat going to do? What is removing it going to do? Okay, so we've gone over our 3 scenarios. Let's get to the math. Go find a calculator. Okay, we're back. I hope we have a calculator. If not, pause the video. Make sure you went and get it. We're going to look at the combined gas law. You can find this formula in your reference table. It's table T, where all the formulas are listed. So you don't need to memorize the formula. Okay. The ones mean initial, right? The pressure, volume, and temperature at the beginning. The 2s mean at the end. The pressure, volume, temperature of those gas particles at the end. Okay. So they're not necessarily going to give you the numbers in order of the formula. You have to be able to know. How will you know? The units. Remember, the units will tell you. So let's take a look and put the numbers where they belong. So we're going to work here. Pressure 1. I want you to think which one of these numbers, A, B, or C, is pressure 1. What unit is pressure? And if you're not sure, your reference table will tell you on the front page. 1 atmosphere. So pressure 1, I'm going to line it up. You do need to put the numbers where they belong. Numerical setup is part of the regions. You get points for setting it up correctly. Okay. Next, I need the volume. So we have 2 left. Which of these is volume? Again, looking at the units. Okay, hopefully you know it's 50 mils. And last, temperature. And notice it's not something you're used to. Not Fahrenheit, not Celsius, Kelvin. Okay, that absolute Kelvin scale. And that is our denominator. Okay, so I've set up the first side. I'm halfway there to that point. I'm going to go to the other side. Okay, and again, I'm looking for pressure. Oh, it's a question mark. I'm going to put X, because I don't know what that is. It's my unknown. Next, I need volume. My final volume, V2, and 50. That's the same. It's the same number. We're going to come back to that. That's interesting. Last, we have our new temperature. Okay, so I've done my numerical setup. I got my point. Yes, halfway there. At 1 point, we got 1 more point to go. Now I want you to think conceptually. What is changing? Okay. Well, the volume is not changing. the temperature is going to change. How, is it going up or down? Right, this is the beginning, this is the end. Beginning, end. Hopefully you're saying it's going up. What do we know about temperature increasing, adding heat? It makes particles move how? You think about it. Okay. Increasing the temperature should make the particles move faster. And if the volume is not changing, right, if that can it's in is solid, then it's going to change the pressure. So the pressure is going to change. Now I want you to think, if it's heating up, is the pressure going to go down or up? Well, think about at the normal temperature, and then when it heats up. Look again, right? Normal temperature, heating up. Which one of those situations you think has more pressure? Right? Beginning or the end? So hopefully you're thinking, oh, temperature's going up, this pressure should go up. So my final answer should be bigger than 1. Right? Temperature's going up, pressure's going to go up in this case. Now, since the volume isn't changing, there's a trick that you should definitely use. Right? It cancels out. Right? You say if you have the same number on each side, if it's a constant, you just cancel it out. So now I have my numbers, and I can just cross multiply, or you can use algebra, whichever method you like. Okay? So I think, again, if you cross multiply, you're going to have 293x and 1 times 323. Okay, so let's try that. Let's say you're going to cross multiply. If you're going to do that, let's take a look at that. So 1 times 323 is just 323. X times 293 is 293 times x. Now I still have to get x by myself, or by itself. So I need to do the opposite. I need to inverse this. This is multiplying times x. I need to divide both sides. Whatever I do to one side, I do to the other. It's going to divide or cancel out. Now x is equal to 323 divided by 293. This is where you get your calculator. 323 divided by 293 equals, right, 1.02389. Do I write all those numbers? Am I going to write that whole answer? No. I have to look at my measurements. I have to round with significance. I can't have a final answer that has all this exactness, and my data didn't have that much exactness. Okay, so take a look. We're going to take a look. We're going to round. And we have 2 sig figs, 3 sig figs. Looks like 2 is our, oh, wait. I have 1 sig fig. So I'm actually going to round, right? So it's 1.1. In fact, I'm going to go back and add a sig fig here just to make my life easier. There you go. So I'm going to add 2 sig figs. I do want to keep 2 in this problem, so sorry about that. 1.0, that's 2 sig figs, 2 sig figs, 3 sig figs. 1.1 atmospheres. We thought it was going to go up, right? Because temperature goes up, makes them move faster, collides more with their container, so it should be more pressure, and it is. It only went up a little, so pressure only went up a little. Always double check. Okay, you're going to be practicing this throughout the week. Good luck.